everyone and welcome to Transformers course video number 7. In the previous videos, we covered the transformer construction, theory of operation, equivalent circuit, exact and approximate equivalent circuits referred to any side. It's about time to speak about transformer performance. So in this video, we are going to cover transformer efficiency. Let's start. To tackle the efficiency topic, we need first to know what are the transformer losses. What are the classification of losses inside the transformer? We have two types of losses. The first one is called iron loss or core loss. So if you have a magnetic core or iron core like this one, so core loss occurs in the magnetic core due to alternating magnetization. So that one due to eddy current and hysteresis. We covered that one in the previous course, which is the magnetic circuit course. But this loss is constant if the supply voltage is constant. The other type, copper loss. When we have a current going through the winding, so copper loss arises from the winding resistance when current flows through them. So copper loss is variable based on the load conditions. So the two types of losses are iron loss and copper loss. So the iron loss is constant and the copper loss is variable. So this diagram here shows that whatever the load conditions is, no load, medium load, full load, the constant loss is fixed value, while the copper loss is variable based on the loading conditions. So what is the transformer efficiency? Let's first define what is the efficiency. All of us know that efficiency is a measure of how effectively a device, such as a transformer or electrical machine, converts input power into a useful output. So efficiency is power output over power input. Regarding the transformer, transformers are known as the most efficient electrical machine in power systems, with efficiencies exceeds 95% in most cases. However, no practical transformer is perfectly efficient or 100% efficiency. A portion of input power is lost due to core loss and copper loss, as explained in the previous slide. So look here, for the equivalent circuit referred to the primary or equivalent circuit referred to the secondary, we have a core loss and copper loss due to these resistances. The figure here shows the power flow diagram of the transformer power. Input power, and we have core loss and copper loss, and we have output power, and that one gives us the efficiency, output over input. So the question now, why we need to calculate the efficiency, or why the efficiency calculation is important. So efficiency calculation is important and required because it helps us to know and evaluate how effectively the transformer is transferring the power from primary to secondary under different loading conditions. Additionally, efficiency identifies opportunities to reduce energy losses in power systems. So this is why we are concerned by calculating the efficiency, and we consider the efficiency one of the measurements for the transformer performance. Let us evaluate the efficiency mathematically. So we are going to use the first approximate equivalent circuit referred to the primary side to find the equations which gives us the efficiency. Firstly, we are going to calculate the core loss or iron loss, which represents the eddy current and hysteresis loss. So P iron equals I core square R core, and that one is consumed in this area. So most of the time that one is given as a constant to the problem, but if we like to calculate it, we can calculate it as I core square R core. Regarding the copper loss, so that one is I2 dash square R equivalent, and R equivalent equals R1 plus R2 dash. So someone said that's R1 plus R2 dash plus R load dash. No, R load dash is the out. So in this case, we are going to say output power or load power is V2 dash I2 dash cosine phi, and phi is the angle between V2 dash and I2 dash. Or you can calculate it as I2 dash square R load dash. What about input power? So input power is output power plus core loss plus copper loss. Or you can say that V1 I1 cosine phi input. What's cosine phi input? The cosine theta V1 minus theta I1, the angle between V1 and I1. So let us put that one in equation form. So eta equals P output over P input equals V2 dash I2 dash cosine phi over V2 dash I2 dash cosine phi plus P iron plus P copper. And phi is the load power factor. We are going to repeat the analysis if the circuit is referred to the secondary side. So for the core loss or iron loss, I core dash square R core dash, and again is consumed in this part of the circuit. For the copper loss, we have I2 square R equivalent, and R equivalent is R1 dash plus R2. For output power, we have V2 I2 cosine phi, and phi is the angle between V2 and I2, or the load impedance angle. So we can calculate output power as I2 square R load. For input power, so input power equals output power plus core loss plus copper loss, or we can say V1 dash I1 dash cosine phi, and phi here is the angle between V1 dash and I1 dash, which is cosine theta V1 dash minus theta I1 dash. We can put it in the equation form. So efficiency here equals V2 I2 cosine phi over V2 I2 cosine phi plus P iron plus P copper. Let us summarize what we did so far. So the efficiency is power output over power input. So we have two circuits now. Equivalent circuit referred to the primary side, definitely first approximation, or equivalent circuit referred to the secondary side. So what is the efficiency? If it's referred to the primary, equals V2 dash I2 dash cosine phi over V2 dash I2 dash cosine phi plus P iron plus P copper. And if it's referred to the secondary, V2 I2 cosine phi over V2 I2 cosine phi plus P iron plus P copper. We feel somehow it's complicated to memorize these equations or to use these equations. Any further simplification for these two equations? So this is what we are going to explore in the coming slides. So let us examine the efficiency specifically at full load conditions. So rated current at full load can be calculated as I2 dash full load will be S full load over the primary voltage, or I2 full load equals S full load over the secondary voltage. So you can find these values in the nameplate, which is V primary and V secondary, and the S. So you can calculate the current at full load. If you calculate the secondary current at full load, you can make the referring. So output power at full load equals V2 dash I2 dash at full load cosine phi. That one, if the circuit is referred to the primary, and if the circuit is referred to the secondary, we have V2 I2 but at full load cosine phi as well. So we can write this one as S full load cosine phi, because we know that VI equals S, which is the apparent power. The power in watt equals VI cosine phi, but the power in volt ampere equals voltage multiplied by the current. So this expression can be rewritten as S full load cosine phi. Remember, we are still in the full load conditions. Copper loss at full load equals I2 dash full load square R equivalent if the circuit is referred to the primary side, and equals I2 full load square R equivalent if the circuit is referred to the secondary side. So we can rewrite the efficiency equation as eta equals P out full load over P output at full load plus P iron plus P copper full load. So we are going to swap power output by S full load cosine phi over S full load cosine phi plus P iron plus P copper at full load. And that one is going to save us from searching that the circuit is referred to the primary or the secondary, because we know the rated power of the transformer and the power factor or the loading power factor. So we are going to search for iron loss and copper loss at full load. Let us summarize what we covered so far. So we have the efficiency at full load equals power output full load over power output full load plus P iron plus P copper at full load. And you can ask why I put P copper at full load a different color, because I said P iron is constant, but P copper at full load will be variable based on the load conditions. So at full load we have a specific value, at another load we have another value. So we can rewrite this equation as, instead of power output at full load, S full load cosine phi. So the equation will be eta full load S full load cosine phi over S full load cosine phi plus P iron plus P copper at full load. Let us take an example. We are going to repeat example number 6 in video number 6. So we have a 10 kilovolt ampere, 2000/200 volt, 50 hertz step down transformer, and we have the parameters not referred to any side. So we are going to find the first approximate equivalent circuit, and this is what we did in the previous video. We have R2 dash and we have X2 dash and we have V2 dash equals 2000 and angle 0 volt. And then we calculated I2 dash, which is 5 angle minus 36.8 degrees, because the power factor is 0.8 lagging. So how to calculate the primary current and primary voltage? Again, please refer to video number 6. So V1, which is the primary voltage, equals 2080.34 angle 1.1 degree volt. And the current in the primary will be 5.344 angle minus 39.7 degree ampere. So we need to calculate the transformer efficiency. We are going to calculate the efficiency using two methods, but let me remind you that the transformer is operating at full load with 0.8 lagging power factor. Method number 1. We are going to calculate power output over power input. So we're going to calculate output power and input power. So for output power, V2 dash, I2 dash cosine phi, or S full load cosine phi, so that one is 2000 multiplied by 5 multiplied by 0.8, 8 kilowatt. So for power input, V1 I1 cosine the angle between V1 and I1. So that one is going to give you 2080.34 multiplied by 5.344 cosine 1.1 minus 39.7, and that one is going to give us 8415.77 watt. So what is the efficiency? 8000 over 8415.77. That one is roughly 95.06%. Method number 2. We are going to use the equation power output over power input equals V2 dash I2 dash cosine phi over V2 dash I2 dash cosine phi plus P iron plus P copper. So we calculated output power, but we need to calculate iron loss and copper loss. Regarding the iron loss, we need to calculate the core current, I core. We calculated that one in video number 6 equals 0.104 ampere. So we can calculate iron loss now, I core square R core. That one is 216.32 watt. Regarding the copper loss, I2 dash square R equivalent. So that one is 5 square multiplied by 8 gives us 200 watt. So we are going to apply this equation, the values. So that one is going to give us something like 95.05%. So they are 100% matching. We noticed in the previous slides that you calculated the transformer efficiency at full load. However, this does not mean that a transformer should operate only at full load conditions. The full load calculations simply provides a useful reference point for evaluating transformer performance. In practice, transformers are typically designed to operate at 80 to 90% of the rated capacity to provide a safety margin and ensuring a reliable operation under varying conditions. To illustrate this, consider the example shown in the figure, where a transformer supplies power to a factory. The table here presents a typical daily loading profile. As we can see, the transformer does not operate at a constant load for 24 hours. Instead, its loading changes from 15% to 90% throughout the day, depending on the factory's power demand. For example, at 8 a.m. to 12 p.m., we have a peak production by 90% loading of the transformer. At 6 p.m. to 8 p.m., we have cleaning, logistics, and so on, by 60% loading conditions. So, this means the transformer efficiency also varies with the loading conditions. While we can calculate the efficiency at any load level, an important question arises here. How do the transformer losses change as the load changes? To answer this, we need to examine the behavior of the transformer losses, core loss and copper loss, under varying loading conditions. As we explained in earlier slides that the losses in the transformer are two types. One of them is core loss or iron loss, and the other one is copper loss. So the core loss is constant value irrespective of loading conditions if the supply voltage is constant. We have another type which is copper loss, and copper loss follows the parabolic format where P copper equals I square R equivalent. This is why we call that one variable loss. The total loss will be the addition of the two curves, and it's clear here that the losses will be affected by percentage of loading, and in consequence, the efficiency of the transformer will be affected by the percentage of loading as well. So how to calculate the efficiency at any load? We know that we have S full load, which is the rated power of the transformer, written on the transformer nameplate in volt ampere, kilovolt ampere, megavolt ampere, it depends. So we have S full load, which equals V2 I2 at full load, or V2 dash I2 dash at full load. If we assume that we have X, which represents the percentage of loading from the full load conditions. So this means X of full load equals X multiplied by S full load. So we are going to substitute in the equation where X multiplied by S equals X multiplied by V2 dash I2 dash full load, or X V2 I2 full load. Let us rearrange this equation because X affecting the current, not the voltage. So X multiplied by S full load equals V2 dash X multiplied by I2 dash full load, or V2 X multiplied by I2 full load. Why I do that one? Because I'm going to consider that one for the current. If we have a copper loss, so that one will be Xi square R equivalent. So I full load square multiplied by R equivalent will be the copper loss at full load, and X square at any load multiplied by P copper at full load give you the copper loss at percentage of loading X. So the efficiency at any load with percentage X of full load is x multiplied by S full load cosine phi over x multiplied by S full load cosine phi plus P iron plus x square P copper at full load. Now I'm going to make sure that this equation is correct. Substitute by x equal 100%. So that one is going to return back to the previous slides we covered, where we have S cosine phi over S cosine phi plus P iron plus P copper at full load. But at any load, we have x multiplied by S and x squared multiplied by P copper at full load. Example. For a 25 kilovolt ampere 2000/200 volt single phase transformer, the iron and full load copper losses are 300 watt and 400 watt respectively. We need to calculate the efficiency at unity power factor when the percentage of loading is 25%, 50%, 75%, and 100% of the full load. So we know the equation now, xs full load cosine phi over xs full load cosine phi plus P iron plus x squared P copper at full load. Given in the problem that S full load equals 25 kilovolt ampere, power factor equals 1, P iron equals 300 watt, and P copper at full load equals 400 watt. So at x equals 25%, we have the efficiency 95.1%. If we increase the percentage of loading at 50%, we have efficiency 96.89%. Increasing the efficiency more, we have at 75%, 97.28%. At 100%, we have the efficiency 97.27%. If you notice here, the efficiency is not increasing up to the full load. There will be a certain increase and then there will be a decrease. If we look for the figure now, I plotted that one using MATLAB, so we have the efficiency curve from 0 up to 100%. It looks that the efficiency at this region is constant somehow. So I'm going to focus on this region only. So we have now the curve shows that we have efficiency increase then decrease. So there will be a maximum point. So we need to search for this point later on. But before searching for the maximum point, we need to look for the efficiency profile versus percentage of loading. From the previous example, we can plot the efficiency versus percentage of loading. As we can see here, we have iron loss, which is constant, copper loss, changing in a parabolic format, and we have efficiency starts from 0 point at 0% of loading until we reach a maxima here or a maximum point. Then the efficiency is going to decrease again. Please note, maximum efficiency is not at full load conditions. Some student made a mistake here. When we are going to ask about the maximum efficiency, they put x equal 100%. But that one not the case here. If that one happened by chance. So the maximum efficiency occurs only when iron loss equals copper loss. We need to prove that one mathematically. So we have here the efficiency function of x percentage of loading. How to find the maximum mathematically? If we differentiate the efficiency with respect to x and equal the value with 0, we are going to find the condition which achieves the maximum efficiency. If we do that one, we are going to find that P iron should equals x squared P copper at full load. I'm not going to do the derivation because that one is going to waste the time of the video. But we need the conclusion that at maximum point, P iron should equals x squared P copper at full load. So x, which satisfies the maximum condition, equals root P iron over P copper at full load. If we substitute in this equation, so the maximum efficiency of the transformer is x maximum S full load cosine phi over x maximum S full load cosine phi plus 2 P iron. Example. We are going to repeat example number 9, but this time we are going to calculate the maximum efficiency at unity power factor. So eta maximum equals x maximum S full load cosine phi over x maximum S full load cosine phi plus 2 P iron. We have the same given, so 25 kilovolt ampere, power factor unity, P iron 300 watt, P copper at full load 400 watt. So x maximum equals root P iron over P copper at full load. So x maximum equals root 300 over 400, 0.866, which is 86.6%. Please note that one is not 100%. So the maximum condition or the maximum efficiency is not occurring at full load point. It occurs at 86.6% of loading. So at x maximum equals 86.6%, so eta maximum equals 97.3%. Please refer back to example number 9 and compare the results. But I'm going to bring for you here the curve which we plotted in example number 9. And if you look for this point, you are going to find a maximum point which is almost occur at 86.6%, 97.3% efficiency. Let us take another example. A 2 kilovolt ampere step-down transformer 440/220 volt is feeding a load with a lagging power factor of 0.8. The iron loss is 45 watt, which is constant, and the copper loss at full load is 65 watt. We need to calculate the efficiency at full load, the percentage of loading for maximum efficiency, which is X maximum, and the maximum efficiency. So given in the problem, we have S power factor, P iron, and P copper at full load. So we are going to use a general equation, which is XS full load cosine phi over XS full load cosine phi plus P iron plus X square P copper at full load. And we are going to substitute by X equals 100% or 1. So when X equals 100%, we are going to find that the efficiency is 93.67%. Eta maximum, or the maximum efficiency, equals X maximum S full load cosine phi over X maximum S full load cosine phi plus 2P iron. So what is X maximum? Root P iron over P copper at full load, and that one gives you 0.832. So eta maximum equals 94.87%. Why you give us this example? I need to show you at full load, which is 100%, efficiency is lower than the maximum point where X maximum equals 83.2%. So please take care. It's not necessary to have the maximum efficiency at full load, and usually it's not happen at full load. Exercise. A 20 kilovolt ampere single phase transformer operating at unity power factor and has an efficiency of 96.04% at 40% of loading and 96.56% at 80% of loading. Calculate the maximum efficiency. I'm not going to solve this problem. I'm going to leave that one for you, and you are going to add in the comments the answer, and we can discuss together the answer and solution. What will I watch in video number 8? We are still in the transformer performance. So in video number 8, we are going to cover voltage regulation. See you in the next video.